All right, you think that first one knocked your socks off. Wait until you see this one. This is a graph of f prime of x. It's now asking us to find one possible f of x. And you know what? We're just going to add on to the end just for the fun of it. Let's also draw f double prime of x just because that's good practice. Okay, now we're going to do the f double prime first because that's going to be a little bit easier to deal with. Okay, so remember that when the first derivative is 0, or sorry, when the slope of the first derivative is 0, that's when the second derivative should be 0. All right, so first we can look at that. So here it's 0, so that should be the 0 of your second derivative. And then here it's also 0, right? That's a minimum, so that should be 0 as well. Okay, so this is my derivative graph. It's telling me about the slope of my original function. And then what I'm graphing now is the second derivative. Okay, and so I look at it here. Tell me about the slope of my derivative graph. It's positive, right? That means that the second derivative should be positive because here the slope is positive, so it should be up here. All right, now what happens after that? The slope of the derivative graph becomes negative. So if the slope of the derivative graph is negative, that means the value of the second derivative needs to be negative, and so it goes negative. Now at some point, it needs to come back up and go back through that point, after which you now have a positive slope for the derivative, and so it goes something like that. Maybe steeper. Yep, should be a nice parabola. All right. So there you go. You now have a graph for the second derivative, and that was easy. It goes from the x cubed. You take the derivative, and you should get something like 3x squared, which is what kind of we expect, a parabola. Now, the harder one, sketch one possible f of x. All right, so we're going to try that now. Now, if this is f prime, and this is f double prime, then that means that f of x, right, this was a square, that's cubed, that means the original one should have something to do with x to the fourth. We're not going to worry about the numbers yet. That's going to come when we do the antiderivative, the integral. But for now, we just need to know that it's a quartic. Now, let's look at the derivative graph. Let's draw a sign diagram for the derivative. Okay, so you draw a sign diagram for the derivative. I've got x-intercepts at about negative 4.8. I've got another x-intercept right here at about negative 1.1. And I've got another x-intercept right here, and we'll just pretend that that's a positive 1. It's close enough. All right, so before this point, note that the derivative is negative. Okay, so negative there. It goes to positive. Between there, the derivative is positive for all of these values, and then it goes back to have negative values again, and then positive. Okay, so this is a sign diagram of the derivative, which means when I look at the derivative graph, it's just telling me is the derivative negative, is the derivative positive, etc. Okay, note that this graph is not the original function graph, so don't get confused. Don't tell me that the derivative is positive for all of this, because it's not. Though the derivative of the derivative is, which is why the second derivative had to be positive there. The actual derivative, which is this purple line, the actual derivative is negative here, which means the original function should have a negative slope. Now you can look at this, and you should be able to tell what the function is going to look like. It's going to go down, and then it's going to go up, and then it's going to go down, and then it's going to go up. So it should go down, up, down, up. Now, at this point, that's all you know. You don't really know anything more than that. And I'm sorry, that's all you can know. That's why it actually says sketch one possible f of x. The problem being is that you don't know how high or how low they go at this point. Remember, if we had started with f of x, how high that graph is, where it is up or down, depends on this transformation up at the end. If it's a +3, it'll shift up 3 spaces and it'll be higher. If it's a -3, then it'll shift down, it'll be lower. But when you take the derivative, what happens to that? The derivative of the constant is 0, which means the derivative doesn't show you how high or low your graph is. It just talks about the slope. It tells you about the shape. And so that's really all we can do, is make the shape. So what I'm going to do is I'm just going to choose an arbitrary point, a random point for negative 4.8. So I'm going to go to negative 4.8, which is, oh, sorry, that should have been negative 5.8, shouldn't it have? Because that's after the negative 5. So negative 5.8. So I'm going to just put a random point on the graph. It doesn't really matter where it is. Okay, so before 5.8, it needs to be going down. After 5.8, it needs to go up. Now, how long does it go up? Well, it goes up until we get to negative 1.1. So at negative 1.1 at this point, that needs to be my maximum. So we're going to go up, just like that. And then it's going to go down, right? Because this negative derivative tells me that the original slope had a negative slope. So I'm going to go down until I get to 1. So I'm going to go down, 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 down. I'm just going to go to wherever I end up at, which is about there. And then at positive 1, the slope now needs to be positive again. So it'll go up like that. Now, your graph may not look exactly like this, and that is completely fine. In fact, my graph, this is not that good. It should probably curve something like this and curve like that, so it looks a little bit more like a nicer quartic function there. And that's, you know, that's a lot of this is just kind of, they want to see, did you put the minimum in the right place? Did you make it a minimum, right? Did you show that because the derivative is negative here and positive there, that the original function had to be a minimum at that point? Did you show that there's a stationary point here where the derivative is 0? Is there a stationary point there? If there is, then is it a maximum, right? The slope here is positive, the slope here is negative because the values are positive, negative, therefore you should make it a positive. Again, right here, there's the 0 for the derivative function. That means you should have a stationary point there. Did you show that it's a minimum? That's what they want to see. And so if you can do that, then you're going to be fine, regardless of how high or low your graph is. Now, as far as the distance between the points, yeah, you can actually get that by using some information that we don't have yet, by using integrals. But for now, we're not going to worry about it too much. All right? And so there you go. You've got your graph. The green one is the original function. That's one possible f of x, which could be lower or higher based off of where you put your original point. And we also, just for fun, did the second derivative, which then should be a quadratic. Note, please, that the second derivative is positive here, which means you should be concave up. So are we concave up? We are concave up until that point, right there. After which we should be negative values for the second derivative, which means we should be concave down. We should be concave down until right here. And so you're concave down, and then after that point, the second derivative is now positive, which means you should be concave up, which we are from that point. So all of these things tie in together. And it's good to be able to recognize all of them, because then you can double check your work and you can make sure that everything is correct. IB expects you to be able to do that, to be able to look at original graph, derivative, double derivative, and be able to put those ideas together. All right? So that's the end of this example, and we're going to do some more in class. How about that?